are going to continue the chapter, and we are starting with the microprogramming. As we can see, the basic concepts are there. We talk about micro operations. We have already seen that the programs that are executed as a sequence of instructions, and each instruction consists of a series of the steps that make up the instruction cycle, like fetch, decode, etc. Each of these steps are in turn and made up of a smaller series of the steps that is called as micro operations. We have also studied the micro operation execution, in which each step of the execution or instruction cycle that can be decomposed into the micro operations primitives that are performed in a precise time sequence. Each micro operation is initiated and controlled, which is based on the use of control signals or lines that are coming from the control unit. So the controller is the data to move from one register to another, and the activation of specific ALU functions. Moving to the micro instructions, every instruction of the processor is translated into a sequence of lower level micro instructions, and the process of translation and execution are known as microprogramming. So we move to the microprogram control unit, which is a relatively logical circuit that is capable of sequencing through the micro instructions and generating the control signals to execute each and every micro instruction. We have already known to the control unit, which is an important portion or part of the processor, which is able to control the whole processes, the memory and input output. So the control unit also issues the control signals that internal to the processor to move the data between the registers and to perform the ALU and other internal operations in the processor. But in the hardware control unit, the control signals are generated by a micro instructions that are used to control the register transfers and ALU operation. So now we have the control unit design approaches, and we can see that how we can use the concept of microprogramming for the implementation of a control unit. So there are two types of different approaches. One is microprogrammed implementation and second is hardware logic implementation. As we can see from the figure, the control unit is there with the decoded inputs. There is an instruction register with a decoder. There is a control unit which is consisting of the timing generator, a clock and flags, and generating the control signals. So this is where the decoded inputs like I0, I1, I1, I2 to IN can be there, like the control signal C0, C1, Cn can be there, and the timing control generators T1, T2, Tns can be there. So this is the approach of microprogram control unit, where the principle is to control the signal values for the each micro operations that are stored in the memory and reading the contents of the control stored in a prescribed order, which is equivalent to the sequencing through the micro operations. Since the microprogram of micro operations and their control signal values that are stored in the memory, this is a microprogram control unit. While we move to the approach of the hardware logic, you can see the principle is the control unit is viewed and designed as a combinational and sequential logic circuit. The control unit is implemented by using any of a variety of the standard digital logic techniques, and the logic circuit generates the fixed sequences of the control signal. So this is the approach that is used to generate the fixed sequences of the control signals with the higher speed. If you move to the microprogram control unit, you can see the idea of microprogram control unit is the control unit design must include the logics for the sequencing through the micro operations for the execution of micro operation, for the interrupting of codes, and for making the decision based on ALU flags. So the design is relatively inflexible. It's difficult to change the design if a person wishes to add a new machine instruction. And the principal advantage of a microprogram control unit is that it will be slower hardware than the hardwired unit of the comparable technology, and the microprogramming is the dominant technique for the implementing units in the contemporary CISC processor. The control unit operates by performing the consecutive control stage that reads to generate the next state set of the control function outputs and performing the series of control memory accesses. In fact, executing a program for each instruction in the machine's instruction set, and the term is known as the microprogram. If we move to the micro instruction sequencing, you can see there are two problems involved in the design of a micro instruction sequencing technique, that is size of micro instruction at the address generation time. The first concern is the minimizing of size of the control memory, and the second is a desire to execute the micro instruction as soon as possible. So there are categories like they are determined by the instruction register, the next sequential address, and the branch. So it is an important to design the compact time efficient techniques for the micro instructions branching sequencing technique. So there are general three categories as follows: two address fields, single address field, and variable format. From the figure, you can see the address decoder, control memory, the control address, branch logics, multiplexer are there. So you can easily understand this diagram. Like we can also see it stands for control buffer register, and the CAR registers is known as the control address register. The micro instruction execution shows us that the cycle is the basic event on a microprogram processor, and each cycle is made up of the two parts, that is fetch and execute. This section deals with the execution of micro instruction, and the effect of execution of a micro instruction is to generate the control signals for both the internal control to the processor and the external control to the processor. As you can see from the diagram, this is the unit of control unit. You can see the LU flags clock are there, instruction register, sequencing logic, control address register, control memory, control buffer register, and control logics. That includes both circuits like internal and external control signals. While we move to the classification of micro instructions, it can be classified in the variety of ways in which the designer must choose the parallel power of the every instruction, like the vertical programming, in which the every micro instruction specifies a single micro operations to be performed, and the horizontal, each micro instruction specifies the many different micro operations to be performed in parallel. Like vertical programming, the width is narrow and there is limited ability to express the parallelism. In the horizontal programming, the wide memory word is there and the high degree of parallel operations are possible. We move to the second compromise, that is used as a two-level controlled storage organization. The output of the two-level memory drives the address register of the bottom level. The nano memory uses the horizontal format and produces the actual signal outputs. The advantage to this approach is the significant saving in the control memory size, and the disadvantage is it is more complex and slower operation, while the microprogramming applications are for the typically large microprocessor systems today, and there are many instructions and associated registers level hardware, so the control points to be manipulated. While we move to the system buses, we can see the system bus is a pathway that is composed of cables and connectors that is used to carry the data between a computer microprocessor and the main memory. And the bus provides a communication path for the data and the control signals that are moving between the major components of the computer system. The system bus works by combining the functions of the three main buses that are named as the data, address, and control bus. While each of the three buses has its separate characteristics and responsibilities, the system bus connects the CPU within the main memory, and in some systems with the label L2 cache, the other system buses as the input-output buses branch off from the system bus to provide a communication channel between the CPU and the other peripherals. While the address bus is used to specify the memory locations for the data being transferred, and the data bus, which is a bidirectional part, it actually carries the data between the processor and the memory and the peripherals. The design of the system bus varies from the system to system and can be specific to a particular computer design or maybe based on an industry standard. So the advantage of using this industry standard in the ease of upgrading the computer using standard components such as the memory and input-output devices from the independent manufacturers. The system bus characteristics are dependent on the needs of the processor, the speed, the word length of the data and the instruction. The size of a bus, that is also known as its weight, determines that how fast the data can be transferred at a time and indicates the number of variable wires. A 32-bit bus, for example, refers to the 32 parallel wires or the connectors that can simultaneously transmit the 32 bits. While moving to the Multibus Organization, it is primarily used in industrial systems. In this structure, the various devices that have different transfer rates can be connected at the same time, and the maximum throughput is maintained by using the technique of multibus organization. If we talk about the benefits of this technique, you can see there are many more benefits this technique uses. In a single bus architecture, all the components, including the CPU, memory, and peripherals, that share a common bus. While many devices need the bus at the same time, it creates a state of confliction, which is called as bus contention. So some of them wait for the bus, while another has control of it, and the waiting wastes time. So slowing the computer down, the multiple buses permit the several devices to work simultaneously, reducing the time spent waiting and improving the computer's speed. So the performance improvements are the main reason for having the multiple buses in a computer design. For the expansion, if having the multiple different buses that are available, it gives us more choices for the connecting of devices to the computer. As the hardware may offer the some component for more than one bus type. For example, most desktop PCs use the Serial Advanced Technology Attachment Interface hard drives, but many external hard drives, if there's a SATA connections are all used, the USB device will let us connect the additional lock devices. We talk about the compatibility and see a computer's components bus design evolves with the new types being introduced after every few years. For example, the PCI, that is Peripheral Component Interconnect, that supports the video network and other expansion cards that predates the newer PCI interface, and the USB has undergone the several major revisions. So having the multiple buses that support the equipment from the different eras will let us keep the legacy equipment such as printer and older hard drives and add the new devices as well. So you can see from the figure, there are buses, bus A, bus B and bus C. The incrementer is there which is attached with the program counter PC. There is a register file, a constant value for the multiplexer, ALU is there, and there is an instruction register, there is IR, MDR, that is memory data register, there is MAR, that is memory address register, which is connected using the address lines. So the multi-core is